Okay, so welcome back. I need to make this very entertaining because we are all sleepy, I guess, after the lunch. Apparently there is a problem with my slides. So for some reason it's not moving. So maybe the
reason is
if you turn it on, it works better. Okay, perfect. Okay, so I think I would like to skip these details about the implementation of the sprinting controller, because I think I gave you the idea, and also the result, you can trust me, it works really nicely. And so this, in the interest of time, I would all this stuff is included in the slide. So if you want to give a look, and it's also being published last year in ISSCC. Now let me actually move to the next topic, so I will have time to give some more entertainment. So we talked about on-chip thermal control, but you know, if you want to do real thermal stuff, you should go to the so-called big iron. Okay, so now to entertain you a little bit more, something about something really, really hot. Okay, so this is a computer, a supercomputer called Aurora, and this is actually being made by an Italian company called Eurotech, and this is the top, actually the top first and second computer in the Green 500 list. So I don't know if you are familiar with the Green 500 list. It is essentially the list, the hit parade of the most energy efficient computers in the world. And this is the way you measure energy efficiency. It's how many millions of elementary operations you can achieve with a watt of power. So the rating of this machine is 3,200 MOPS per watt. So it's 3.2 gigaops with a watt. The whole machine consumes 30 kilowatts. So it's okay. It's not a huge monster. And it is 30% better than the third ones. Okay, so it is a very, very energy efficient machine, but nevertheless it is a hot machine because this is a supercomputer. It's not a sensor node. So I like to say Italians do it better, at least in high-speed cars and energy efficient supercomputers. Okay. So this is the architecture of this machine. So why it is so energy efficient? So it's a very interesting machine. I actually enjoy a lot looking into this. So the architecture is not so different from a supercomputer, a generic supercomputer system. So you have a node which is usually made with off-the-shelf high-performance chips, and we'll see which chips are used in this one. Then these nodes are integrated into a backplane, which essentially provides a high-speed communication, which is at the level of a chassis. And then you add to the chassis the cooling, and you integrate various chassis into a rack, typically piled up vertically. And this becomes your system where you can have multiple racks. So this is not so strange. What is really interesting about Aurora is that the machine is liquid cooled. So this is the rack. After the cooling is added, and the cooling is actually water, or actually coolant, which is a mix of water and other stuff, flowing in and out through the chassis, but actually, as we will see, is actually flowing in and out of the node boards. Okay, and so what makes it more energy efficient? This is not a new thing. If you look at the IBM supercomputers, Blue Gene and so on, they are liquid cooled. Okay, so this is not new. So what it makes it so energy efficient? So first of all, why liquid cooling is very energy efficient, it is actually shown here. And essentially, I have a slide in next one, but this is actually showing the what you get in terms of energy efficiency. So this is an air-cooled machine, and you have on this axis you have the power, and on this axis you have the CPU temperature. And as you can see, you can get with lower power at same performance, you can get with lower power liquid cooling and keep your die temperature significantly lower. And of course, the hotter is your water, then the more power you spend overall, but you have to consider that you are not spending so much power to cool the water itself. So it's the idea here is that if you actually can operate a system at reasonably high temperature, you will still have power savings with respect to air-cooled system if you liquid cool it, and you can save quite a lot of power outside the machine because you don't need to cool the water so much before it enters into the system. And why liquid cooling is better than air, I think this is very convincing picture. And in mathematical terms, you can say the heat capacity of water is 3,500 times more than the heat capacity of air. In other words, this is the amount of water that you need to take out similar heat than with this amount of air. Okay, so you need to flow much more air to take out heat than water. Okay, so this is why fundamentally why water cooling is more efficient than pure air cooling. And then there are other interesting arguments on why water cooling with high temperature water is more efficient than water cooling with low temperature water. And the argument is essentially that you don't have to put so much effort in cooling the water with the chiller, but you can just do a heat exchange with ambient temperature water or ambient temperature air to get better energy efficiency overall. So
MW is megawatt or milliwatt? The example for heat exchanger.
This one here is a megawatt. Yeah. And this is a very large scale machine. Okay. Okay, so the other thing, so liquid cooling is okay. Hot or warm water cooling is also an interesting idea. And the third idea is more related to mechanical engineering than electrical engineering, and it's the way actually the machine is cooled. And they have a cold plate here. And the cold plate is, you can imagine, like two layers of metal separated by a flat and wide channel. And in this channel, water is pumped. So you have this one, in this cold plate, water is circulated. And this cools this cold plate. And the hot chips are tightly coupled to the cold plate. So the water is flowing very, very close, so there is no heat spreader here. You can see the water is flowing very close to the chips, and there are two phases here. These are, so it's cooling on two phases. So the chips are on one phase and also on the other phase. And this is where you have all the hot components. Then inside the node, you also have another board, which is not cooled because this includes components that are not so hot. So this is the picture, and this you see this gray stuff here. This is actually the half of the cold plate, so the water will flow here. This is the channel. So the water will flow here, and on one side of the cold plate, you have GPUs, or accelerators. This machine can be fitted with NVIDIA K20 top-level GPUs or with Xeon Phi accelerators here. And on the other side, which is not shown here, but it's shown here, you have the general-purpose computers, which are the high-performance Xeon multi-core processors. Okay, so The other differential thing about the liquid cooling here is that you have a very smart and tightly coupled mechanical system that removes heat very efficiently through the liquid.
Excuse me. In this scheme, there is no need for embedded PCM phase change material.
No, because you are using much more in this case you don't need it because you are using water that is removing heat very fast. Okay, so what did we do with this interesting machine? So you can imagine this machine like a problem of monitoring and of tracking the thermal state of this machine multiplied by several orders of magnitude the scale of what happens on the chip, because this machine has literally thousands of chips. Each one of them has thermal management issues on their own. So it's a really multi-scale problem. And in fact, what we developed in the last few months, so this is all unpublished material, it's very fresh stuff. We developed a complete data collection backend, which is, you can imagine, has a widely distributed sensor system that acquires temperature and power consumption of all the elements of these machines. And we start, of course, from the chips themselves. So there is a monitoring infrastructure made for the cores. And actually, at the cores, for what we are concerned, we can measure load at the single core level. So here we have CPUs that include 8 cores. So each CPU includes 8 cores, and each board, which is a node, includes 2 CPUs. So we have 16 cores per node. And the power monitoring available in hardware is per core. So we have load, CPI, hardware frequency, and the temperature per core. And then at the chip level, we can measure the temperature, the power consumed at the chip level of the cores of the entire chip, including also memory controller, and also of the DRAM that are external chips. For the MIC accelerators, we have less fine-grain monitoring because we can only measure the temperature of the die. So it's a single sensor, temperature sensor for the MIC accelerator, which features several tens of cores, but we only have a 1 temperature value. And then we have several board-level temperature values. And we can also measure the power intake of the various chips. Unfortunately, for the MIC, we don't have per core temperature or power measurements. And then for GPUs, we have a similar, it's quite similar in terms of infrastructure for monitoring with respect to MIC. So just to give you an idea, MIC is more or less similar to the SCC that I was describing in the first part of the talk, but as you can see, Intel is only using a single sensor for the whole chip, which gives you much less resolution. So with respect to the talk that I was giving before, we have at the chip level much less resolution in this machine, but we have many more nodes. So here the power management will be more at the chip level or at the big core level, and not at the single core in the MIC or in the GPU, because of lack of information. So we can collect all this information, and we can also collect information about the power and consumption and of at the rack level and at the room level. And this at the room level will also include the power consumed by the cooling and the external power supply. And this is needed because to make the whole thing energy efficient, you have to consider the whole picture. So not only the machine, but also how much power you spend in the cooling. So then you have to integrate this with the traditional data collection front end that are usually oriented to performance. So they only provide information about the load. And together now we have the possibility to monitor the load, the power, and the temperature together. And then we can start doing modeling and extraction and control later. So there are some interesting points I will briefly show you, because this is just, we are just putting down the infrastructure to do the control. But there are some interesting points that would make this a very interesting research problem. First problem is, the first interesting point is this is related to energy efficiency, and this is performance versus power. So this is actually power efficiency or energy efficiency, and then you will see that performance versus power actually goes slightly down, but not so slightly. It's more than between 15 and 20% down when you go to high frequency, which basically means that if you want to have top frequency, you have to be ready to give up in energy efficiency. And this is actually a very important point, because it will point out to techniques that try to achieve the best overall system performance without pushing the single course too much into the energy inefficient region. That is when you are actually putting too much frequency requirements here. This is not accounted for so far in the standard power management. So overall, what you would like to achieve is some sort of a thermal aware job allocation, where you actually have a job list coming in. You have this collection of heterogeneous computational resources that are CPUs, GPUs, multi-core accelerators. And then you want to pose this as a problem, which is how you would distribute the job on the course, and how fast to run each one of the course. So you have a double decision: how fast to run the course, and which course actually to use, and which core actually to leave in the low power state. And of course, your constraints is that you want to achieve the desired performance for this work, and maintain a temperature at a safe level, and reduce the energy. So it's quite a complex problem. It's quite a complex constraint problem, and it's a very large size problem. So currently we have a simplified optimizer that is still not running on the machine, but we are trying to scale it up to the level of this machine size, and still we are not there. And we are trying to solve this problem with an approximate ILP solver to actually try to be able to solve it online. So today we are not there, but it's a very interesting set of problems. Let me skip this slide because it gives more details on something that is not there, but I just want to make sure that it is understood that the problem is highly multi-scale, because you have to decide which subset of the machine to use, and within a subset of the machine which type of cores to use, and you have to do it over time. And even within a chip, you have to choose which one of the cores and how much frequency try to squeeze out of each one of the cores. So you have at least 3 levels of scale in the type of decisions you have to make on this type of machine. So it's really interesting, and it's really complex. So the other point that I never mentioned in terms of control is that since this is actually cooled with water, you have another degree of freedom, which is on the cooling, how you can control the cooling. This is a machine where you don't chill the water before it enters, but you have still a control variable from the cooling viewpoint, which is how fast you would push the water in. So what is the pressure and the actuation pressure of your water flow, which also dictates how fast you will remove the heat. And the other interesting point is that since you don't chill the water, this is not only dependent on the workload of the system, but is also going to be dependent on the ambient temperature, because if you push in water that is warmer, because outside you have 40 degrees, then you will have to work harder to get the same thermal performance at equal workload. So this actually makes it a mixed problem where you have an exogenous variable like ambient temperature and endogenous variables like how much work and what is the pressure that you want to give. And so this makes it quite a complex problem. So let me give you some interesting views of the first measurements that we have done, because I think this shows that this is a really interesting machine. So this is actually showing on this axis, these are the nodes. So each one of the boards is one tag on this axis, and this is only looking at the cores, not looking at the accelerators. So we are only looking at the Xeon, the general purpose processors. So remember that we have 8 core processors and 8 core CPUs and 2 CPUs. So here we have up to 16 cores per node. Okay, so these tags are the cores in each node, and these are the nodes. So we have 74 nodes and 8 core CPUs in each node. And this is the average of the load, the workload, over 24 hours. So you will see immediately that there is a very widespread load, and this is actually dictated by the way the workload has been allocated to the machine. Just for future references in the next slides, the bottom here are the racks, the nodes that are in the rack close to the floor, and the top here are the nodes that are in the rack close to the top. The second point that you will find interesting is that the water comes from the bottom, because the pumps are in the bottom and it is pumped up to the top. Okay, so we'll see that having an influence in a few seconds. So this is actually looking at the CPUs, and here I'm showing that the CPUs in the various nodes are not homogeneous. I have half of the rack that is made with the CPUs that are in a reasonably low speed bin for a high performance computer. So this is 2.1 gigahertz CPUs, and the second half of the rack is 3.1 gigahertz CPUs. Okay, so these CPUs can run at different frequencies, and this is the actual maximum frequency that you can get from the CPU when it's operated at the maximum frequency. And actually, this one is the average frequency that you get because of the workload. We are not controlling the frequency. The power manager that is running on the Linux system on this course is actually deciding the frequency using on-demand governor. So the on-demand governor is essentially an automatic control loop that decides the frequency based on the workload. And you can see that this is kind of working, because when you have a higher workload, your average frequency of the processor in the node is actually going up. Now, there are some interesting points here. You see that here you have a hole, and this is actually a node that where it's turned off because it was under maintenance. So there are a few nodes that are not used because they are off. And you see that the on-demand governor, if you look at this line, you will see that the average frequency of each core, we are here within a node, and these are the average frequency of each core in a node, in a CPU, and you see that this is not constant, okay? And this is the on-demand governor that if the processor, the core, is loaded differently, will give a different frequency, and overall you see that the average frequency is not the same for all the cores in the same CPU. And here you see another very interesting point. Even though the maximum frequency is supposed to be 3.1, you see that these columns are actually having average frequency that is higher than the maximum frequency. How is it possible? This is possible because these chips feature turbo boost. So actually here the machine is massively using turbo boost, and is actually overclocking the chip for such a large fraction, overclocking some of the cores in the chip for a very large fraction of the time, such that you even see that the average frequency of these cores is higher than the maximum rated frequency. And this is actually another thing that you will see very interesting, is this is actually half of the processors are in boost mode, while the others are almost completely unloaded. You see, these are running at a very low average frequency. Okay, so it's a very unequal load even within a single node. So now this is the CPI, and this is actually non-idle clock periods per instruction executed. So higher is worse and lower is better, because it means that it's doing good things, it's doing many instructions in a clock. And as you can see, it's surprisingly high. Okay, these are high performance processors, so it is surprisingly high. It means that in average you have 5 clocks per instructions here. And you see that some of these processors actually have a very low, which means good CPI, but we needed to understand why there is this difference. So this is not well understood yet. Okay. Now let me show the temperature, and this is where some very interesting things you will see. So here I have 16 sensors, and the reason is that each core has its own sensor. There are 2 CPUs, 8 core each, and each core has a sensor, so there are 16 temperature sensors. And these are all the temperature readings, and this is the average temperature over 24 hours. So let me show you a few interesting things. If you look at node 41, which is the one that has turbo boost, okay, so this one that I'm pointing here, you see that there is a very, very significant spatial gradient in the chip. So this means that this the hottest CPU in the chip is almost 20 degrees hotter than the lowest temperature CPU in the same chip. And this is actually strongly pushed by turbo boost. So there are very significant spatial gradients in the chip, and this is quite obvious from these measurements. Now, if you compare the 32 and 33 nodes, which are here, okay, with the 41, which is here, 32 and 33 are both at very high load, okay, but is a more well spread load. 32 and 33 have a better spread load, while this one is using turbo boost. We don't know why it's doing it, but we are seeing it, and you see the difference in temperature. So essentially, this is actually telling us that this guy is doing similar work as this guy, but with much lower temperature. Okay, so it is a clear indication that turbo boost is a highly temperature risky temperature. From the point of view of temperature, is highly risky. And the last point I want to show you is that here, these nodes have a very similar low load as these nodes. And look at the difference in temperature. Even though they are all very low, at very low load, these guys are around 20 degrees, and these guys are around 40 degrees. Okay? And this is actually telling us that there is some non-uniformity in the cooling, because these guys are almost at the same temperature of the coolant, while these guys are much higher, even if they don't do much. So it's a non-uniformity, which means that we'll need to take care of this spatial non-uniformity when doing control. Okay, so this is, I think, I have some other interesting points, but I just want to stop here because I have still a second part of the talk that I want to cover, where I have some interesting things. So looking forward, we will have more and more thermal design power bound chips, and more dancing on the thermal red tape solutions like sprinting and so on. And active cooling solutions will get from the rack level to the board level, like in Aurora, and then I strongly believe they will be coming also to the chip level. Then we have seen a trend toward increasing architectural heterogeneity. We have seen this CPU plus GPU and many core on the chip. And 3D is coming up. We have quite a lot of work on thermal control for 3D chips, but I'm not going to describe it because of time reasons. And we will see also more sensors. So as you have seen, research chips already features many more sensors than production chips. And the trend is going to be to have more and more sensors. And the trend toward on-chip power supplies makes me hopeful that we could even have fine-grained power gauging, power monitoring, thanks to on-chip power supplies, which makes the system more controllable, but also more complex to handle from the control viewpoint. And the trend is toward many small but inaccurate temperature sensors, so with all the sensor calibration problems that I briefly described before. So what we need, looking forward, is need highly scalable controllers and capable of dealing with multi-scale stiff thermal control problems where you have multiple time constants that have to be orchestrated. And also we need to bridge the gap between dispatching how to dispatch the workload, and control, how then you control what happens after you dispatched. Today they are too much decoupled, and we need to have a more comprehensive view, a more holistic view. So now let me go briefly into warm systems. So the difference between hot systems and warm systems is very artificial, but allow me to make this differentiation. And the differentiation here is that we assume that we are working far from the thermal rundown point, but we still have to worry about reliability. So we still have to worry about not running the chip too hot or at the too high temperature for a long time. And so this is to achieve a reliability target. And this is actually motivated. These are the slides showed before, but there is only one point here, and is actually showing that if you do a stress test with the two very different temperatures, then your degradation is going to be 5 times more in the chip that is operated constantly at the high temperature compared to the chip that is operated constantly at the low reasonable temperature. So this is not 10%. It's a really major decrease in lifetime. So the point I was making at the beginning is that it's relatively simple to recover reliability margin. The thing is that you should run the processor slower and at a lower voltage, because both frequency and temperature and voltage are aging faster your chip. But then you get performance loss. So what people have tried to do is to put some reliability models into the thermal controller, into the resource management, into the controller. So not only directly monitoring the temperature, but also monitoring a function of temperature, of voltage, and of the characteristic of your technology that will give you a reliability estimate. So you do dynamic reliability management using a model that correlates what you have in terms of temperature and voltage and what you would estimate in terms of your reliability model. So the initial work that was presented a few years ago was on single core and did not care too much about user experience, and use a reliability model to estimate the chip lifetime based on an offline characterized reliability model. So we try to extend this work to actually try to give a better performance feeling to the user, to extend it to multi-core, and to actually use sensors to refine the reliability model as the machine moves into aging. So the idea is actually quite simple. This is the baseline architecture we started from. So task requires a voltage and a frequency, and you have your controller. Your controller has a reliability prediction based on the past history of the system, so it has memory inside, and based on the information about the flow of information coming from the core that gives essentially the history over time of what frequency and voltage the core has been run at. So if then you have a requested reliability, which is 10-time reliability with 10 years reliability with 30% of failures, say, and this is your request. And then this comparison with, so you take the history of your frequency and voltage, you put it into a model, it will give you a reliability prediction, and then your reliability, you compare it with a reliability request constraint, and if it is not meeting the constraint, you will have to bound the frequency and the voltage so that you will not overuse the core and exceed the reliability. So this seems quite a reasonable approach, but the main problem is that this is a very slow changing function. And so if you start to bound this statically, bound the operation of the core based on this function that changes very, very slowly, because this is a reliability function, it's not like temperature, it changes with much lower speed than voltage or frequency and temperature, then it means that for a very long time, until you make some corrections, this max will strongly bound the performance of your chip. So as a user, you will see, things going very nicely for some time, and then when this guy kicks in, you will see the chip going slower, and it will go slow for your time scale. You are reasoning in a matter of seconds. This guy reasons in a matter of day, so you will have your cell phone go slow for days. Okay, this is quite unacceptable. Okay, so in other words, this is where you would have your requested temperature, your requested voltage and frequency. This is the profile. Then this guy will kick in and will bound your frequency and voltage, and you will get much less than what you expect. So your performance decrease will be very significant. So the idea again is a multi-scale. The idea to overcome this limitation is a multi-scale approach that tries to do some borrowing of reliability margin based on the fact that you don't need in a mobile phone or reactive system, you don't need maximum performance for very long times. So essentially you have a short-term controller that could relax the long-term reliability bounds for some time and give you the capability of borrowing some reliability for the future and then try to get it back when you are not so much loaded. So you have a short-term controller that does borrowing, of course with the controlled way, because if you always borrow, you will end up to die in debt. So you don't want to borrow too much. And but since you borrow, you can go over the times where you need a lot of cache or a lot of frequency so that you don't decrease your user experience. Okay, and this is applied on several cores, and several reliability predictors are adapted core by core. And this is actually quite important because it gives you the opportunity to possibly shift work from one core to the other if the core is not so much aged or it doesn't have so much borrowing ongoing in that time. So here the concept is shown here. So you are actually trying to give what you are asked and to just bound when you are seeing that you are borrowing too much. Okay, so try to minimize the performance degradation by borrowing, and then try to get back what the system has borrowed during the high inutilization period. This is actually what happens if you do some experiments. So actually you see that the state of the art, which is the red line, this is the requested workload. The green line is the requested workload. So the green line has this type of peaks of high reactivity needs, and once you have finally aged, so this is when you are already in the aged, you already have aged. So the basic controller is actually cutting always the peak of performance, while our controller is trying to do its best to give what the requestor gives. What the requestor asks for, but of course sometimes it cannot, like here, because it's over. You cannot borrow too much over a single period of time. So okay, so this is quite efficient in giving you a better responsive systems, and at the end, since you get back what you have borrowed, the reliability penalty is actually not so not measurable with respect to the baseline controller. So what we are doing now on this area, we are actually implementing this on a real tablet computer. So this is actually applied on the Qualcomm S4 development tablet. And we have implemented all the modules to estimate reliability, to do the borrowing, to measure the temperature and so on, which is needed by the model. And actually, we'll see that essentially the things that you have to do frequently, you can do quite fast. And the thing that you can do at a much slower rate, like adapting the reliability model, take some more time. like this one, but this is the long-term controller, so it's this long-term controller is a very relaxed requirements because it has to run with the sampling frequency of hours or days, so a few milliseconds over such a long time is not such a big problem. So from the implementation viewpoint, it can be implemented, and actually we are going to publish this type of results. Now, what is the real challenge in this area is to actually provide some solid experimental measurements on the fact that you are not compromising the reliability, because on that case you will need a very long measurements or accelerated temperature tests and so on. So one of the challenges when you are doing reliability work in this type of in the wild environment with a full platform working and so on is how to prove that you are actually not decreasing the reliability here. So if you have ideas in this area, I would really be happy to hear what you think about how to experimentally validate on real test benches this reliability experiment, these reliability techniques. So finally, I have a few minutes to go into the last part of my presentation, where I want to discuss some things related to cool silicon. So here the concept is that we are now going towards these very low power systems where the motivation for that, this is not my slide, this is by Intel, and they are basically saying, if you look at your leakage energy, and if you look at your dynamic energy, when you actually start to raise the voltage supply, you have that your dynamic energy going up. Also, your leakage energy goes up significantly. And then if you lower too much, then you have very low dynamic energy, but then your leakage goes up because you are being so slow that the leakage current integrated over the period of time becomes dominant. So this, if you sum the total leakage, the total power, the sum of these two contributions, you have this nice single minimum curve, which tells you that if you operate very near the threshold, you will get very significant energy savings compared to operating in the standard region that would be like, here, okay, well above threshold. Of course, the price to be paid here is that you are slower, significantly slower, but you are, you can recover some of the speed you need by having parallelism, and overall your energy efficiency is actually better, significantly better. So Intel, among others, ARM is also preaching to the same choir, and everybody is now looking into this near threshold computing. Which is also called a dim silicon because it is not lighted so brightly, but it's just doing what is needed and try to do it very slow. So near threshold recovers between 5 and 10x energy efficiency, which is very good. But then if you go so low in terms of voltage, then you are very near the threshold, and the memories will bite at you because memories are suffering when you go near to the threshold. So there are some techniques where you differentiate the memory arrays with different voltages, some specialized memory design techniques to extend the voltage range at which the memory will work. A lot of people are working on this. I'm not to talk about this. Then you have, of course, performance loss. And the idea is that to use multi-core parallelism to actually recover some of this performance loss by spreading execution on multiple cores working slowly. It's like quite well known. Now the big problem is variability, because when you get closer to your threshold, your variability is very much enhanced, and your temperature dependency on your variability due to temperature is really significant. So we are going to deal with this problem, and actually we want to have an architecture that tries to compensate variations. So let's see what is the basic idea. So your critical path is strongly affected by temperature, and this essentially shows a little bit more quantitatively as how strong. And near threshold, this is actually showing for a given frequency, if you want to achieve a given frequency of operation, and this is the worst case temperature and the best case temperature, what is the difference in voltage that you have to give to the processor to achieve a given frequency, and you see that this is a big gap. So if you want to make a thing completely temperature unaware, you will always have to run the processor at this safe voltage that will ensure that you work at the prescribed frequency every time. But all this is loss in energy efficiency because you are working at a much higher voltage to guarantee that you always meet the performance, the frequency target. So we need to do something else about it. And so let's discuss it in the context of a parallel architecture. So we'll consider a multi-core architecture where we have multi-clusters, and we focus on a single cluster. And this is actually a design that is derived from a design that was on silicon in ST Microelectronics. I was responsible for this design for a few years. And now we are looking into derivations of these designs for near threshold computing. So the idea of this design is that the cores are sharing level 1 memory. So this is multi-banked memory. And these are the cores. And the cores are sharing the level 1 memory. And through an interconnect that is performing spreading the traffic through these memories. And so each core can access all the banks. And this is emulating a multi-ported memory. So overall, this is where the critical path is in this system, because it is a global interconnect structure. It is combinational because this is a L1 memory, so you don't want to wait for this memory. So this you cannot wait many clock cycles to access your level 1 memories. So this is a combinational logarithmic multi-stage network. And it is spread over the chip, and this is where actually most of your critical paths are. So if you do the analysis of your critical paths and you factor in the temperature effect, your bell of paths, your critical path, your path statistics will shift forward with temperature, and then you will end up having at the critical temperature you will end up having a lot of timing violations in your path, which basically means that your chip doesn't function properly. So the way to recover this is the standard way to recover this is to make the voltage higher, but then you will burn all the power advantages that you have in running near threshold. So the problem is that you will have some because of variability, you have some of the path failing, and so the idea here is to make the architecture capable of readjusting to paths that are critical and they are failing, to readjust locally by actually inserting locally some pipeline stages where you see some failures happening. So essentially, you don't raise the voltage of everything, but you try to add some delay tolerance in the paths that are failing. Of course, you need to determine which are the paths that are failing, and there are several ways to do that. So we'll discuss this next. So the idea is that you will, in a sense, retune your interconnect to add some pipeline stages only where you see that some of the paths are failing. And of course, you will lose performance, but we lose performance locally because you are not retuning all your interconnect. You are only retuning the paths that are failing in your interconnect. So only some processors and some memories will become slower, and of course, gradually everything will become slower. But this is much smoother transition, and the performance penalty is not so drastic as if you run everything at lower speed, or if you slow down everything by inserting pipeline stages everywhere. So the idea is that you have this control unit that under software control will run self-tests to see if you are actually failing. And you want to run these control units under a temperature profile. So when you see your temperature changes, And you remember, this temperature is not changing because of self-heating. It's changing because your chip goes outside and there is the sun, or comes inside and it's cold. So you see your temperature profile. You have your temperature sensor measuring the temperature of the die. And whenever you transition a temperature threshold, you have to do this check and reconfiguration. And so you can here conditionally insert a pipeline stage at the boundaries of the processor or at the boundaries of the memories, so you have a longer path, a longer pipeline, and here you will have much more time to complete your combinational travel across the network, so you will have capability of adapting to the increased delay by adding 1 or 2 pipeline stages. Okay, so this is the overall the basic idea, and then you have to build your variation tolerant interconnect. You have to build your test units that would test if paths are failing, and then you need to add your control logic to do temperature monitoring. So this will go on a time scale which is quite coarse, because temperature doesn't change in a microsecond. So and so this will actually trigger the system into self-test and reconfiguration whenever a temperature threshold is crossed. Okay, so this is the fundamental idea. Now you have also some tricks to reduce the cost, and so here the idea, so here is how it will work over time. So you have your initial boot, where you do your determination of what type of delays you want in your interconnect. Then you have the monitor keeping track of the temperature, and you execute the program. Now let's assume that the temperature hazard has been detected, so one of those temperature gaps has been crossed. So you have to move the program into safe mode, stop it, do the detection, reconfigure the interconnect, and then start. And in this time you will lose performance because your program is idle during this time. Okay, so you want to minimize the time this happens, because this is going to give you performance loss, blocking, and then you will of course have performance loss also here, because you have reconfigured the network, but this is unavoidable while we want to minimize this. So there are some various tricks that you can do. So for example, caching temperature thresholds. So caching the reconfiguration that you have done when you have crossed the threshold. So when you see the threshold again, you will reuse that configuration. And this will speed up the reconfiguration and the adaptation phase. And actually, if you compare with what happens if you just scale down the frequency of the entire cluster to make sure that you adapt to the slowest path, the percentage of improvement is really significant, because here you have to slow down everything, while here you slow down only the paths that are actually failing. So it is an adaptive solution. It uses architecture and runtime monitoring, and it lowers the cost with respect to a solution that is unaware of the architecture and is adapting the frequency just in a reactive way for the entire cluster. Now, well, this is actually showing that with respect to worst case design, if you project this over a system that will work 1 year in continental temperature where there are big fluctuations, this system will actually deliver much better performance than a system that is designed at the worst case and will have to work only in the worst case assumptions, or even a system that will adapt entirely based on temperature and not on a fine grain like we suggest here. So one last point before I go toward the closing. What is the area overhead of all these? Actually, these control units are very small. They are simply, self-checking type of logic and very small control logic. So from the point of view of what your area overhead for all these is really small. So it's actually quite affordable. Now, one last point I want to make before I close is what if instead with temperature the circuit goes faster? Instead, this is actually what sometimes happens. For example, when you are near threshold, you may have thermal inversion, and actually at high temperature, thermal inversion means that high temperature your circuits are not slower but are faster. So you say, well, no problem, because if it's faster, I will still meet the timing constraint. Well, you meet the setup timing constraints. You don't meet the hold timing constraints. The hold timing constraints happens when you have a path that is propagating too fast, and then it could be clocked in the next stage of the pipeline before the clock of the pipeline has arrived to the next stage because of clock skew and things like that. In fact, when you design a chip, you work a lot to fix the hold timing constraints as well as setup. So you may have actually a chip that malfunctions because it becomes too fast. So this is showing what happens. So, you know, if you, for example, you are in thermal inversion, when you go at low temperature, you will have the error because of a slow path. But, you know, if you are at high temperature because of thermal inversion, then you can actually have the error on the very fast path because of hold critical path violation. Okay, so the solution is similar to the one that we have seen before, but instead of adding a pipeline stage, you add some delays on this very fast path. And you add it on a programmable way, simply as we were adding a flip-flop to, in the previous case, to add a combinational, to add a pipeline stage. Again, this has to be configured using temperature thresholding and temperature trip points. And in this way, you can also adapt to circuits that fail because they become too fast because of hold time violations. So this is just a starting branch of research. There are many ways to actually adapt architecture to temperature variations. And I think that here there are a lot of opportunities really because of the relatively low speed of external temperature variations compared to the relatively high speed of self-induced, self-heating temperature variations. Okay, so let me draw conclusions of this overall lecture. I think that the goal of my lecture was to give you some practical examples and some fundamental ideas and to show also that the temperature awareness is required both with hot silicon, so server chips, high performance embedded chips and supercomputers, and this is actually to prevent a thermal runaway. It's also needed for warm silicon to avoid running for too long and in an uncontrolled way at very high temperatures so that you will limit your lifetime of your silicon. And it's also needed for cool silicon because of temperature-induced variability and the need to control it without giving up all your energy savings. So technology advances actually are pushing for having more control in our chips, in our silicon systems, because we have a trend toward fine-grained operating points, and these are essentially the three variables that you can control: VDD, frequency, and even body bias. And body bias was going away for some time, but now with the silicon on insulator technology coming back in fashion, this body bias is becoming also very effective now. Coming back in 28 nanometer technology in SOI, this is a very, very interesting. We are doing quite a lot of work in this area. VDD is also, was out of fashion because they say, well, what we can do with VDD. But now with the near threshold is coming back in fashion, and also with on-chip voltage regulators, it's coming back in fashion too, because you have much more fine-grained voltage regulation possible if you start pushing on-chip voltage regulation like Intel is doing in its latest products, and also IBM is doing that. So these knobs are not going away, and actually they are staying in, and they are becoming very, very interesting. Active cooling, as I showed, I discussed liquid cooling, but there are a lot of other things that are being explored, like thermoelectric converters, so cooling using thermoelectric effect. There are people that are trying to miniaturize thermoelectric converters to try to extract heat using thermoelectric effect. And this is also quite interesting. And of course, there is all the active micro cooling and nano cooling area that is explored, for example, by IBM using their silicon channels technology. And of course, there is a traditional fan speed to be still managed, but there is quite a lot of work on this already. Then there is the possibility of having phase change materials and enable or high capacitance thermal systems to enable sprinting. And so all these techniques will push for more control, multi-scale, non-linear, and so on. And finally, we still have to fully understand the complex trade-off between temperature and quality of service. So I think that maintaining energy proportional is a fundamental requirement. So all this I talked about, I did not talk about energy proportionality, but it's a fundamental requirement. So could give another talk about energy proportionality, but let's keep it in mind that whatever we do here, we should not violate the energy proportionality. So more things you do, more energy, but in a linear way, not a super linear way. And multiple time scale is obvious that is happening, and this will require controllers that have multi-layer orchestration. So overall, I can say that the fun is just beginning, and thank you for your attention.
Okay, any questions or comments?
I propose to use the mechanical engineering terms when we are talking about the heat transfer. Hot silicon, warm silicon, and cold silicon, not cool silicon.
Okay, that's a good comment. Yes,
and,
I can.
For your water cooling system, may I know the dimensions of the water channel? Are you using microfluidics effects or you are in macro scale?
Okay, so first of all, I wish this was my cooling system. It's a cooling system made by a company, and I'm only getting familiar to it, so I cannot be extremely detailed on that. From what I've seen, these are channels that are I've seen the enclosures, so you can. The overall metal enclosure is like a little bit more than a centimeter thick, and inside the channels are I would say a few millimeters, 3 and 4 millimeter channel. So I cannot tell you if it's laminar flow, turbulent flow. I don't know. This is what I've seen. Okay.
Will be laminar. If they decrease the channel dimensions, they will be in the microfluidic state and heat transfer enhancement.
Yeah.
Is that high heat transfer rate in lower
So
size?
Your comment is that they should make it narrow,
yes,
thin, so that you have laminar flow and better heat transfer.
Yes. Yes.
Yes.
And second comment, they can use the commercially available refrigerants instead of water.
Oh yes, yes. This is actually an interesting. This is actually an interesting point, because I've seen that even IBM is not using a commercially available cooling liquid, but they are mixing water with some coolant, some antibacterial. So I don't know why they are not using.
But they are about one century experience in mechanical engineering for enhancement. The heat transfer they can use.
Yeah.
They don't need to invent the wheel again.
I think it's a very good point.
Thank you.
Okay, any other?
Thank you for your wonderful talk. And I just learned some new technology that's using the embedded thermoelectric cooler. Do you think this kind of cooler will be more better than liquid cooler?
Okay, so we actually did some experiments in collaboration. I had a postdoc visiting the group of Sherif Reda in Brown University, doing work on microcooling on the chip surface. So I think that we did some experimental work on that. So took the lid off and tried to put the microcoolers on the chip and so on. So okay, currently I decided to stop this because it didn't seem so promising. and not because of the fundamental idea, but because of the microcoolers themselves. The energy balance is very poor. So essentially, to extract heat efficiently, you have to put a lot of power into it. Okay, so overall, I think the energy balance, if you look at how much power you have to put in the microcoolers to extract heat efficiently, is overall bad. I mean, you can. So where it could pay off is if you can miniaturize the granularity of the microcoolers, because then you could have active microcooling, which is energy inefficient, but only on a very small area of the chip. And if you assume that there is a hotspot, then if the microcooler is activated precisely where the hotspot is, then it could extract very effectively heat, even at a high power cost. But since it is on a small area, it will be effective. But this is not how the technology is today, because the microcoolers are big and they have losses, and from the mechanical viewpoint it's very difficult to couple them on the surface of the chips. So there are a lot of mechanical material engineering details that need to be fixed before this technology becomes, in my view, practical. But there are companies that are working on this.
But some research say that the thermal gradient, if the thermal gradient is more higher, then the leakage power will be more higher than the liquid cooler and fan cooler, air cooler. Just only, they cannot lower down the thermal gradient. They just cool the whole chip. So this kind of electrics.
Yes, I agree. I mean, this is the point, right? If you can differentiate the cooling strength in different points of the chip at a very fine grain, then these techniques will become very interesting. Now, there is also some very interesting advances in the micro liquid cooling, using silicon channels, where you can actually, there is Professor Atienza who has been working a lot in this area, and he has very interesting results, and is working in close cooperation with IBM that has the technology to make the channels. So I don't have a personal experience, experimental experience in this area, but according to what I've seen, it seems that also with liquid microcooling you can differentially cool different areas of the chip.
Because there are some papers show that if you are using the thermoelectric cooler welding, you can, if you add the leakage power and the power you going to cool it together, the thermoelectric cooler can be better than fan cooler.
Yeah, I mean, I think that at this point it seems to me that this technology is less mature than the other two, but I'm not saying that is a dead track. I'm just saying that currently it is, I see that there is much more fundamental work to do in this area than in liquid cooling and in these more traditional thermal control techniques. But I think it's a good topic. I'm not saying that it's a bad topic.
Thank you very much.
Okay, let's thank, one more question. Final question before the break.
You mentioned that the liquid cooling should go could cover pretty much all application, if I remember properly. To what point you think really it will go? I can understand on the cloud, on the supercomputers, on desktop even, because it's already there.
Yes.
But I can hardly imagine that it would get in the cell phone or stuff like that.
Yes. No, I don't see. I mean, frankly speaking, I don't see how, but unless people come up with really disruptive technologies, I don't see how liquid cooling could go into the cell phones. Okay, so I think it will have to stop to stationary equipment or semi-stationary equipment. I think that if I see how big is this laptop, I think that with some good engineering, it could have some liquid cooling inside, but. I think the mobile phones, tablets, the form factor is, and so while on these ones, I think that I saw it already happening, maybe not in such a, let's say, academic and disruptive way like I presented it here, but phase change materials and enhanced thermal capacitance tricks are already in place. Because if you see, for example, how the tablets are made today, there is a lot of ingenuity in mechanical engineering and design to make sure that you can spread the heat over the whole surface of the tablet without having the hotspot effect, not in the chip, but in the overall enclosure. So this is actually, there are tricks to improve the heat conduction and to actually give more thermal capacitance to the chip so that it can work for a longer period at very high speed, which is what you need if you have to start a browser or to download a page very fast and things like that. So I think that these techniques will actually penetrate quite deeply into the mobile phones. I'm pretty sure that I also read some rumors that they are starting to use carbon layers to improve the thermal conductivity. So I think that so if you ask me, the active cooling using liquid will stop at the stationary or semi-stationary equipment, while the phase change materials and so on will actually go into the mobile space.
Okay, with that, let's thank the speaker again.